can't give you overview of the whole toolkit. I'm just going to give a brief description of how the various acoustic model classes are organized, just to give you a flavor of what is meant by the code is modular and parts that don't need to know about each other, don't know about each other, those things. So just to reiterate, the things that we support currently, it's mainly the standard maximum likelihood training of acoustic models together with SGMMs, and in the standard maximum likelihood framework, we have the usual linear transforms like LDA, HLDA, MLP, STC. We also support speaker adaptation. Currently, FMLR is, we have tested it in the recipes. MLLR code is there, it's unit tested. There's still, I need to write, somebody needs to write the executables and run them. So MLLR is not yet in the recipes, but it's almost done. And both, MLLR obviously has, it's with regression trees, and FMLR has two variations. One is it's just a global transform or with regression trees. This is the point which Dan briefly mentioned, that we had some discussion whether to support things like genome type systems or BBN type models, where and for now things are fairly simple. We decided not to do it now. Maybe if the need is felt in future, and sometimes we also, through the course of this development, a couple of times we thought it might be good to have a system like that. But currently, when we say GMM, it's a very specific thing with means and covariances, and I'm going to just briefly also say how the GMMs are implemented. And yeah, the similar thing with SGMMs. We also have the FMLR adaptation code for SGMMs, a little bit. There are a few results we had previously published which are still not in this new code base, but they're going to be added soon. So this has already been talked about. We have a GMM class, and it knows really about nothing else other than what it contains, that is the parameters. And there is the acoustic model class, which is just a vector of GMMs, and for implementation reason, it's a vector of pointers, but I mean, that's not a interesting thing. But the green arrows in the slides would signify this technical term called knows about, where which is it could be so we have avoided as much of inheritance as we could. Most of the time things are not inherited. If a object needs to keep track of another object, it's either by keeping a const reference, if that's the case. Otherwise, specific methods will take just pointers and modify that object. So knows about is in that sense that you can think that if you have to write the code, you have to include the header for this other thing, right? So the GMMs are parameterized using the natural parameters, which natural parameters in the sense of the natural parameters of an exponential distribution, where if you write out the likelihood calculation, you get these two things, that there's the mean times the inverse of the covariance, and the inverse of the covariance are the natural parameters of your GMM. And the reason for doing that is then you can do the likelihood calculation using just two matrix vector multiplications, because if you have diagonal covariance systems, you have your you will have the mean times inverse covariance is a vector, and say you have 5 components, or how many? Yeah, 5 components, and you have your data vector, and you'll just do this two matrix vector multiplications, right? And there are BLAST routines for doing that. Obviously, level 2 BLAST is not the most optimized thing, but I mean, it's still a nice way of doing things, right? So, a graphical overview of what Dan has already said, that we have this acoustic model class, but when it interacts with the decoder, it interacts through this decodable object, and the decoder knows only about this decodable interface. And for each type of acoustic model, we need to implement a specific decodable interface for that model, right? And the decodable object is the one which also knows about features and just essentially does the likelihood computation. And this is exactly how the decodable interface looks like. So when I said we avoid using inheritance, this is the only exception, which would be when we have interfaces, which we have only like few for features, for decodable, and a few other things. And these are actually pure interfaces. So that's what we, that's the only case where we inherit. So as you can see, it's fairly simple. The main function is the likelihood computation, and the decoder can know that whether there are no more frames, and yeah, how many states essentially you have, right? So for every other model type, you then inherit from this and implement these methods, right? So that was the decoding. For training, we similarly have an object for storing the accumulators. And for the GMMs, and in the same way that the acoustic model is just a vector of GMMs, the acoustic model trainer is just a vector of objects which train the GMMs, right? And
These are not the real class names. There's no compiler that will allow you to have space in a class name.
yeah, yeah. Okay, yes, sure. Yeah, my slides are not compilable. So, um, yeah. uh, and the red arrow means that these classes will modify those classes. Obviously, modifies implies it also knows about, and typically modification, it doesn't keep any an object of the other class. It has a method which will take that object and do the modification. So how do we do adaptation? Adaptation for that, say for feature space MLR. So it's, if it's global, it's implemented as a simple matrix, and the matrix doesn't need to know what it is, right? It's only the estimation which makes it FMLR. So the estimator knows about acoustic model. It knows about regression tree if you're using regression tree, and if you're using regression tree, the FMLR object has just multiple transforms. And similarly, so the FMLR object then, however, doesn't know about regression tree, this concept. It just has a bunch of transforms. It's a decodable object which knows how to interpret those things, right? So similarly with MLLR, obviously that has to know about the acoustic model, and the MLLR can either, you can take an acoustic model and tell it, give me an adapted model, so it will just adapt all the means and give you a new model, or it can do it lazy, so that you can, so the decoder will ask the decodable to get the likelihood from an adapted model. The decodable will query the MLR object, which then will see if it has already computed this mean. It caches the mean. If not, then it will take the mean from the acoustic model and do it lazy, that then convert it, right? So which is how you would use it in practical situations. So the SGMMs have very similar structure. It's again, yeah, there is a decodable. The SGMM, oh, it's that should say S there instead of GMM, right? And the SGMM class, the SGMM model, it has this UBMs, which that's why it needs to know about the GMM classes as well, right? And just for convenience of coding, the SGMM for the GMM classes accumulators, and the updating class is the same. For SGMMs, they are different because there are many update methods used in SGMMs. So yeah, and things to do next. So so the first bullet point, the FMLR basis for SGMM, is already published, like now, like what, 2-year-old work almost. It's in the old code base. We need to put it in the new one. It's partially done. Then a couple of days back, Dan presented this symmetric extension of SGMMs. symmetric encode. Some people keep on asking what symmetric means. So that's also partially done, and then as Dan mentioned, like we are waiting for lattice generation to be finished, and we can add all the discriminative training things. Yes, there were thoughts and discussions and debates on this, on supporting multiple feature transforms. Currently, you only have global transforms, and they are just put into one chain.
Which were the regression classes then that you're looking for? What are those for?
Regression class, yeah, you can have regression classes for FNLRs, but then you can't compose it with any other transform which has multiple transforms as well. So yeah, so when I say
feature space that would define the other transforms. Well, I suppose we don't currently have other multiple
no,
transforms.
no.
Which is the class.
So that's the thing with it, multiple feature transforms. And okay, there's two multiples here. It's first of all, for each type there are multiple transforms, and then multiple such types composed together. And I don't know whether we will feel the need for it, but when we feel the need for it, we'll think about how to do this. And probably it will be handled in something like a decodable object level, because nothing else needs to know about how to compose these things. So that's the end of brief overview of the acoustic models. Any questions?